name's Tom. I've been playing around with IoT for a couple years now. Before doing all this, I was like a cloud architect. I spent a lot of time specifically working with AWS. Then just kind of got into everything, really bridging the gap between kind of the software world and then the physical world is really interesting to me. So I'm going to start off with a demo for something real basic here. And let me figure out if I can flip to another tab. But I will invite you all to go to, if you're interested, go to a website. It's itbrainstorm.com. It's on your phone if you want. Or you can just follow along here. So just to kind of prove to you guys that this works. Bring it up online as well. So what I kind of built for my demo is a little card reader. And how this works, on the back of these are like magic cards if you're interested. I put a little RFID sticker on the back of 3 different ones here. And then, so each of these has some information on it, embedded in it. Here I have an RFID reader, and then that is just jumper wired over to a Pi 0. The Pi 0 right now is actually hooking off my internet here. I didn't trust that we have Wi-Fi. And from there, it's going up to the AWS cloud. And from there, the web app that you can open up on your phone, what I have here, has a WebSocket connection that is listening for updates. So we can take something, I can take this red card here, tap it, and red card shows up. Okay, so you think of this isn't very practical in itself. You think this is kind of how if you ever scan into a turnstile at work, it's a similar system. Right? White card, tap it in, you can see it would take like the person's information, send up to the service, figure out if they're allowed to come in the thing or not, and then the door's open. Right? So that is my little demo of the power of IoT on AWS. Now I got to figure out how to get back to the slides. All right, cool. So the agenda. Demo. Nailed it. We're done. I'm going to talk real quick about MQTT. It's a protocol for sending data around. That's primarily how all this stuff is going. Once we have the background for that, we're going to get into how AWS IoT factors into it. And within that, we're going to talk about a couple of different things. We're going to talk about AWS IoT Core. We're going to talk about IoT Rules Engine. And then touch on how the security works, all that, if you want to set this up yourself. So, want to kind of get temperature of people in the room. How many people have worked with AWS? Sweet. Nice. How many people have worked with MQTT? All right. Yeah. Okay, great. So we talked about how the demo worked a little bit. The magic behind how all these different things communicate with each other is MQTT. MQTT is a messaging broker. So MQTT is a messaging protocol. Stands for MQ telemetry transport. MQ, I think, is message queue. That's one of those things that there's like a bunch of different answers online for. It's a pub sub protocol, which means that you can publish to a topic or you could subscribe to it. And it was primarily designed to send telemetry data between things. So it's something like what you would see on the CAN bus of your car. All different things are sending information about your braking system, the angle of your steering wheel, everything like that. It's all being sent through MQTT. So basic concept is you have a thing. In our case here, this kind of the whole Raspberry Pi RFID reader is a thing. Then you have an MQTT broker, which is a system running somewhere that it can communicate to. The thing can publish a message to it, and the thing can also subscribe to messages coming back off that broker. These messages are JSON objects, which are just key value pairs. So you can take this thing, we'll say it's a humidity and temperature sensor, and it takes a reading, and then it will send it over to this broker. It'll say something like the temperature in the room is 72.9 degrees, the humidity is whatever, and the MQTT broker is going to take that information and then fan it out to anything that might be listening to it. MQTT has a global namespace. What this means is that your thing, like that temperature and humidity sensor, sends that information to the broker, then it fans out. So if you imagine a world where you have 5 or 6 humidity sensors in your room, they're all sending stuff to the MQTT broker, and all the things that are subscribed to all these messages are getting all the different messages, and it's just kind of a mess. It's noisy. Okay? You have this huge spider web of connections going on, everything's going around. So how does MQTT solve this? They have an idea called topics. Topics are strings. So again, so there's a global namespace in MQTT. You can publish with a topic and you define it. You can kind of organize this well. So you would say that I have a thing, it's a DHT sensor, and the ID of it is 001. It's the first of my many sensors. So I push that out, and it's kind of like the subject line of an email. So this goes out, the body of the email is your humidity information.
Reddit for things.
Yeah. So on the flip side of it, you can subscribe to a topic. So any device hooked up to this network can then listen, and you'd say, whenever a message comes through that has the subject that matches, that has that topic, like I want to know specifically what happens on DHT 001, then I'll do some action on it. I'm going to take that temperature and humidity, I'm going to do a calculation, I'm going to do whatever I'm going to want to do with it. That in itself is kind of useful. Where it really starts to shine is that you can subscribe to topic groups by using a wildcard characters and asterisks. So what that means is now I can have some compute resource sitting on my network, and whenever any of my DHT sensors, any of the 10,000 of them that I have set up, send a message, they can work on that. So by namespacing things right, you can kind of start to build out this hierarchy of all your different components throughout your house or your factory, whatever you're building up. So we kind of show a little architecture here. So we have some DHT sensors. This is digital humidity and temperature. LDR is like a light detector resistor. So that's going to tell you whether or not the light's on in the house. Those are all sending messages to an MQTT broker. And this is a program that's running somewhere. And that, again, just kind of knows how to take these messages and fan them back out to everything. Realistically, what's going to happen next? You take all this telemetry data, and then you have compute listening to it. That's figuring something out. So in this world, you have temperature and humidity, and your light. You send it there, and you want to figure out, should I send a text message to Tom to let him know that the humidity is out of whack and the lights are all on while he's on vacation? Okay. So your compute is kind of taking all that, figuring out what to do with the information. Then it sends a message back to your MQTT broker. Then you can have other things going on that are listening to that state of it. So, should the LED in the house start blinking? Like, yes, it's a disaster zone in there. That's a basic state flow. Everything on this left-hand side is mostly going to be like telemetry data, raw data from sensors, and everything on the right-hand side is more like a calculated state. Right, so that's all cool, and that is all something that you can do at home. How does AWS IoT enable this? Well, your compute and your MQTT broker, these are all something that they're pretty lightweight. It's something you could run on a Raspberry Pi, staying at home on your network, anything like that. You can have a Linux box in your closet doing all this. But the reality of it is the power can go out of your house. The operating system that your MQTT broker is on needs an update. You have to take some downtime to do all that. You have to unplug it because you only have so many power outlets, whatever happens. So you have to manage all these MQTT is how you could kind of shift that responsibility off of you and put it up into the cloud. And since you all know about AWS for the most part, I'll just kind of glaze over it. The idea of AWS is there's a whole bunch of managed services that you don't have to take care of. You just know that like AWS has an MQTT broker. You don't need to update it. You don't need to make sure it's running. It's just always going to be there. So switch it over to AWS. Then over the service called AWS IoT. That takes the place of the MQTT broker. It's always going to be there. Then you have your other AWS resources that you can feed into from there. So once you have AWS going, what else is in there for you? There's databases. You could see a scenario where you would want to take the temperature and humidity, and my highlights are not showing up well, but every time one of these comes in, you want to add it as a row on a database. So you can just take all this, split it up into columns, and add it to the database for you. And it's all done with a pretty simple integration. You don't need to figure out how all this works. It's just in the, there's like a GUI for all this. We'll set it all up there. You can do event-driven compute. AWS has a service called Lambda. It is where you could define a simple function. In this case, like calculate the heat index, how hot the room actually feels compared to the temperature based off the temperature and humidity. Every time one of these messages comes in, we just want to run this single function and calculate something and send it back out. So that's all done. And it's one of those things where instead of keeping a bash script running, pulling your network, you only have to pay for the 5 milliseconds that this function is running. You don't need to worry about managing the operating system under it. It just spins up, does the computation, spins it back down. Think about it. So in this case, every time a message comes in, you basically translate it into a function call. You go from there. You can do notifications. There is a service called Simple Notification Service. SNS is really similar to MQTT. It uses a lot of the same ideas. There's publishing, subscriptions, there's topics, and there's more endpoint types. So you can take a message, route through SNS, and all of a sudden you can send emails or text messages based on this. So whenever the humidity is out of the fan, send a text to the person in charge of it. And then I haven't really spent too much time on this, but AI and machine learning are a big thing here. There's something called SageMaker. You can throw a bunch of data into the system, train some machine learning models off of it, and then whenever you get a message coming through, again, temperature and humidity, you can throw it against a model saying, based off of what I've been wearing for the past couple of years and the current stuff out here, what are you most likely to feel comfortable wearing? Like, is it a short stay or not? Just, I don't know. I had a couple of contrived examples out of temperature and humidity. Okay, so we're getting to the end. How do we integrate with all these things? IoT has a rules engine. So this sits on top of that MQTT broker, and it's always kind of listening. It's SQL-like. So you see, if you're familiar with that language, you'd see something like this: select star from star. What that means is whenever you have messages coming through that MQTT broker, no matter the first star is which fields to take, the second star is what topics will come. So we want to take all the information from each of these different fields we want to take. So you publish stuff to our DHTs and to our LDRs, like our temperature and humidity and our light thing, and we just want to pass everything right on through. So on this rule statement, it's going to act on everything that comes through the MQTT. That's not super useful unless you just want to dump everything into a log somewhere. And maybe this isn't the opposite order, we can kind of go, but now you can look and say select star from a certain topic group. So every time something gets pumped to one of those DHT topics, then we'll act on it. So in this case, only one of them's going to come through, and it's that device ID here, the one to the DHTs. The LDR is getting ignored. Similarly, the next feature is this first field here, where you can just take, say, the temperature information from that DHT. So you can start trimming your data down. If you had 10 fields here, but you only want the temperature, then it'll query it all down. That is how that hooks up. And I'll talk briefly on IoT security and how you set this up, specifically about how this will demo. So we have two main connections happening to the IoT service while this is going on. We have the scanner system here going to AWS IoT. Then we have the browser communicating with that. The scanner works over the MQTT protocol. And that is secured by what's called an X509 certificate. So it's a certificate that sits on the device. You think about it like the device is kind of flashing its badge and going in. Like the only way for that cert to end up on that device is for someone to put it on purpose, so you trust it, and it's good to go. The browser works a little bit more complicated. That's hooked up through a WebSocket, which is a connection we see a lot. And that's handled through a product called Cognito. That's where you could, so in the case of the browser, everybody that was unauthenticated, anyone who gets on that app has access to all of my topics there, and that's how that's something. But Cognito is an identity provider, which means that you could force people to sign in. Like, I could sign in with my email address, verify that I'm me, and then Cognito takes care of permissions and will only let me subscribe to the topics I'm supposed to. And that's how you can start narrowing things down. So if you're building a product out where I should only be able to know the state of the light bulbs in my house, you can handle all that through the Cognito authentication. This is just more of what I was explaining. There's the X509 certificates. So certificates and the Cognito side, they both kind of delegate not only what topics you can subscribe to, but what can happen on the AWS side once it's there. So the scanner can talk to IoT, and the scanner can update the database, but it can't go into an S3 bucket and delete all of my information. But you can use that to kind of fine-tune all your controls and get into your security side. Cool. So that is kind of the whirlwind tour of my IoT reader. I've got 2 code repositories up in GitHub. They are right here. There's one for the stuff that is running on the Pi, and then one for the React app that is running on your phone. There's my information. I'm Tom Horton, Thomas P. Horton on just about everything. I'm pretty consistent about it. Reach out. I'm on the Slack channel too if you have any other questions. And yeah, that's my last slide.
So,
Sure.
I'm thinking of Corbin. I'm also recovering from a cold, so I apologize for hoarse voice and any coughing. So,
It looks like it's up again.
okay. I had space from turn off the Chromecast. So yeah, so today I'm going to be talking about hardware reverse engineering for IoT devices. So exactly, if you have like an IoT device, how do you open it up? How do you figure out what's inside of it? How do these components inside of the device talk to each other on the PCB? And then on top of that, how do you actually dump information on the device? So you want to figure out if it's securely storing your password inside of it, or if it's securely handling your data that it sends over to the network and it's not sending it over to some sketchy third-party app server, whatever you want to figure out what's inside of it. And then on top of that, I'll cover some more advanced things on how do you do a more active attack on a hardware device in order to get into double secrets that has protections on it, like DRM or any kind of encryption. this is mostly from a high-level point of view. So for the debugging communications, I'll go into a little bit more in depth on what pieces you buy specifically and how to perform it. But for the
Hopefully that's not your problem.
No, yeah. So for the hardware attacks, that'll be a little bit more abstract, just because it's kind of complicated to go into it, since it would involve a lot of electronic engineering theory, and I don't want to put math up on my slides because no one likes math in PowerPoint presentations. Yeah. So I guess about me, I'm a security consultant at Leviathan Security Group. Yes, I have a computer science background, so my hardware stuff is kind of self-taught. Feel free to yell at me if I have something that's not quite exactly correct. It's not always easy to find information about a lot of this stuff online. And I guess hobby-wise, I like mechanical keyboards a lot. I'm a huge coffee drinker. Seattle Coffee Works is my favorite in the area. And then I guess how I got into IoT is sort of my first year in computer science at university. I worked on a summer research project on that Roomba at the top right here in coffee, the Nerf gun, where we were designing an app store for robots that interact with the real world. Looking at how can you write an app store that doesn't do like drive towards my owner while running the chop vegetable app with a knife, because that would not be a good idea. And additionally, I worked with Arduino a bit in a super mileage vehicle building club, where a group was looking at getting telemetry from a vehicle's engine and just kind of storing it all on an Android device to display to the driver while he was driving, and then also after the race be able to look and say, okay, there's a huge fuel dip in this area, let's try to figure out what was going on there exactly. So that's kind of the extent of my hardware stuff. We're coming out into security stuff and picking it up. I think I should start with safety first, because depending on what you're doing, it can be dangerous. The kind of rules of thumb, I asked one of my coworkers what his rules of thumbs would be for not messing with things. Devices with more than 1 kilowatt can be dangerous. Don't poke around at those probably. Anything with a capacitor larger than your fist can go boom. There's something called dielectric absorption. So if a capacitor is charged for a long period of time, it won't actually decharge to zero all the way. It'll absorb charge from the air, so it can still go pop even if you think you've unplugged it and are playing around with it. So basically don't play with big things as your first projects until you're more familiar with the electronics background. And then a lot of devices now will have anti-static protection, so static is still important, but it's not as bad as old devices where even a small amount can trigger things to not work anymore. They have like grounding things you can buy where you just wear like a wrist, a thing around your wrist that's put into a grounded mat, and that is probably what you should use if you're going to touch something so you don't accidentally short out a circuit anywhere. And then finally is lithium batteries also go boom, so unplug them and take the leads of them if you're going to be messing with anything that has a lithium battery inside of it. That's basically probably what you'll run into if you're looking at a lot of devices. And then as far as your don't regrets when you're getting into it, cheap soldering irons are not good. If you try to solder with a cheap soldering iron, it's not going to work right. You're just going to get more frustrated and probably have to redo everything. So if you're going to buy a cheap one, you should buy a cheap soldering iron that can at least accept good tips and buy a good tip for it. And in the same vein, buy cheap solder and flux because it's hard to get that to melt correctly, and your solder is going to be really messy and not good. $5 multimeters, as nice as they look on Amazon, also are not a good idea because you will not get consistent results. It'll read the same thing and it'll give you big choices between it. And good ones like $50, $60. So if you're a starter one, it's like $50, $60. So it's not a super huge investment. And then also, don't start with a modern cell phone or something really expensive as your first electronic reverse engineering experiment, because you risk breaking it. And you don't want to buy another one and use $300 and ruin it in 5 minutes. So yeah, that is common good first example is to start with a cheap router, like a $40 router or something. And that's probably the start. So now I'm actually going into things. The first thing you need to do when you have your device is obviously open it up so you can look inside of it. And short of like taking a big hammer and breaking the plastic and pulling out the PCB, you should probably just try to find screws. They're usually hidden underneath stickers and those little rubber like feet inside of the devices that they stand on. So you can try like, if you don't know how to take apart the device first, like try looking underneath the stickers and underneath those rubber feet to see if you can open up the device just with the screws. There's also what's called snap fit joints, which are those things that when you push two pieces of plastic together go click. And yeah, so they have those, and they have little shims you can buy that you can just like slide in there and push them in so you can open it up so they aren't snapped together anymore. A good kit for that is the iFixit kit. If you're not familiar with iFixit, they tear down all the way up to like cell phones and take pictures and tell you how to take apart devices for yourself and like do your own repairs. So they sell I think it's like a $90 kit that has a whole bunch of like screwdrivers, shims, and basically everything you need for 90% of devices you'll look at. And then also, yeah, the cell phone repair kits are iFixit ones. And then also a rule of thumb if you've ever built IKEA furniture or anything, if you're disassembling it, you should probably take pictures of the screws or like sort them in buckets or something, so at the end you don't have a whole other like device worth of screws left over. It's always sad to figure out, especially since IoT devices tend to be smaller, so you won't necessarily be able to visually tell easily which one's the one that's like 0.1 millimeter shorter than the other one and won't screw in all the way. So, yeah. And then once you actually start to try to open the device, the next step is just open it, like crack it just a couple centimeters first and make sure there's not those cables in between the top half and the bottom half. Because if you just like pull open the device apart, you might pull out some electronics that you didn't need to. So, yeah, just pop it open like a centimeter, make sure there's nothing like connected between the top and the bottom halves. And those ribbon cables generally have blocking where like you squeeze the side of the tab or push a center thing, and that's what those shims can also help like push those together if you need. It can get kind of annoying if it's not near the hinge where those ribbon cables are trying to squeeze them together though, but you won't run into that unless you're looking at something more complicated generally. And also, just as a measure, if you're looking at a really protected device, there are devices that contain tamper detection. So they'll try to detect if you open the device, and will actually clear out security data when you open it up. So the way that a lot of those work is they'll have a little latch that when you open it up, the latch will be triggered or released. And when that latch is released, it'll say, okay, send a signal over to this chip and erase, zero out all the data, whether it's like a password or some kind of secrets or whatever they want to protect. You won't run into that unless you're looking at higher end devices generally. I don't even think consoles are doing that for a lot of things yet. So, but it's worth noting if you don't want to zero out something that'll then break the device. And additionally, in the same vein, devices that are meant to be shipped to other customers or like that are like a smart meter outside, they'll tend to have like tamper tape or some kind of visual identification on the outside to let you know whether or not it's open. So the easy example of that is the warranty voided peeled stickers on something. So there's ways you can remove those that I'm not exactly covering here, but essentially the stickers, a lot of them different kinds of solvents. So if you look up acids and stuff for the different stickers, you can actually peel off and then re-stick back down if you're very careful. Yeah, so now that we got out of the way of opening a device, what exactly is inside of it? So most of the board is uninteresting from a reverse engineering point of view. What you tend to care about if you're looking for like what data is being stored is you care about the firmware, you care about the CPU itself, and you care about any storage devices. And luckily a lot of those tend to be bigger chips. So basically you can look for the big square chip, and that probably is going to be your CPU, if you know what a CPU looks like. Additionally, most products don't use their own, they don't build their own chips, they buy off-the-shelf stuff. So those have markings on the back of them, and you can go Google markings and look up what the chip is on. So an example of this is firmware tends to be stored in a type of chip called a spy flash chip, and WinBond is a famous manufacturer of those. So if you look up WinBond and then the chip ID, it'll be clearly written. You need a magnifying glass probably to read it, but it'll be written on the back of the chip, and you can go Google it, and it'll tell you, here's the chip, here's what it does, and here's some specifications about it. Additionally, the PCB itself is marked, so you'll want to look for letters etched into the board. Things like the IC or pads marked RXTX, and I'll go into what all that acronym is in a second with more visual examples. And yeah, so the different things that you'll run into for buses is I2C circuits, the integrated circuits, and those are low-speed devices used to talk to sensors. Like so, humidity sensor would be something that would probably use an I2C bus, or an EEPROM, and basically it has data, SDA, which is just the data line, so that's how it transfers the data to each other, and SCL, which is the clock, which if you haven't had a basic electronics class, like the clock basically keeps the devices in sync with each other. So it says my zeros and ones are going to come at this rate from so so it'll send zeros and ones at this speed. A SPI, serial peripheral interconnect, that's a moderate speed, so that holds flash with bootloaders, where bootloader is the first thing that runs when you start up the device. And it's a little bit more complicated than I2C, so it has MISO, MOSI, so that's master in, slave out, and master out, slave in. And the thing that's different about I2C and SPI is that with SPI you can have multiple slaves underneath the master. So you basically have a master bus that can say send a command to one or all of these components. And so it has SS, which is which device am I sending information to, and then the master can send information down one line, and at the same time the slave can send information back up another. That's why it can be faster speed, because it has two lines to send back and forth rather than one shared line. And yeah, you don't need to know the specifics too much for the basics. Yeah, and then JTAG is actually the most complicated of all of these, even though I'll just get into that one later when I have the picture. But yeah, it's used for debugging, and it's a standard, and that there's those 5 standard pins, 5 standard buses, but people add on to it. So I'll show you the connectors later. But yeah, so as I mentioned earlier, basically what you're trying to do, one of the biggest things is try to pull off the firmware, because that's going to hold all your secrets about your device. So the firmware usually consists of configuration, so it'll tell what chips are on the device. It'll have bootloaders, where a bootloader is what starts up when you hit the power button. That's the first code executed that loads your operating system and runs all that code. It has the file systems itself that stores all your data, your files, your folders. It has the kernel for your operating system, and it's not uncommon that they try to save space, and rather than have them nicely packaged up into this is config, this is the kernel, it'll just be a big pop of a file that you'll need to extract and try to figure out what the file is. So now we'll get into more practical, like how to actually do things. So, so for debugging hardware, these are basically the two chips I would recommend as like, for DIY to basically communicate to a device. So there's the FT232H, which is about $20. It's beta proof, and there's the Hydra Bus, which it's sold out right now, and I don't know when it will not be sold out, but it's like $40, and it has more features than that T232 that I'll talk about later. But essentially, these devices let you connect to like a SPI bus and do SPI communication directly in between, or do UART, and I'll just talk about it as I go. Another one you'll see online a lot is a bus pirate, which it's a little bit outdated now, which is why I don't recommend it as much as these other two. The FT232H and Hydra Bus cover the same functionality a bus pirate would, except they're cheaper, so no reason to go for that anymore. Yeah, so I mentioned earlier that SPI flash is where firmware is stored a lot of times. So that's basically the kind of chip you're looking for when you're looking for firmware. And the easiest way to read off of it is they literally sell these clips that you can clip on, and it has those pins at the end. So each of those pins you would hook up inside of those leads in there, and then you would program the device to say, okay, in hole 1, 2, 3, 4, up to 8 or whatever, I'm connected to a SPI flash chip on pins 1, 2, 3, 4, 5, 6, 7, 8, and perform the SPI protocol. So the software to do all the specifics is pretty much written for those devices. You just need to make sure you orient the clip on the right way and have the right firmware running on your chip, your debugging chip. And then those plug in via USB to your PC, and slide. Okay, I'll talk about UART in a second. Yeah, they plug into your PC, and you can run some software that tells you to perform communication. And the problem with trying to read a SPI flash directly with a clip is that sometimes your SPI flash chip is connected to other components on the PCB. So when you try to, in order to read the chip, you need to provide it power for it to be able to operate and send you its memory. So if your chip is located like in the same circuit as other devices, you might put more power through the chip than the chip can take, and you'll start melting things. So we've definitely run into some products where the amount of current we had to send through this chip in order to power up the rest of the board, in order to allow the chip to be read, would have like started melting the cables, and so we were like, yeah, we need a better way. So if that happens, one of the next steps you can do is you can literally take this hot air gun and it blasts hot air at it, and it loosens up the solder joints. So those little pins that connect to the board. So you heat it up enough where you can pull it off very carefully and not pull it off and bump into everything else that's also heated up at the same time. And once it's pulled off, you can literally just, they sell these things called TL8662 Plus. They have readers for different kind of packages, and you just take the chip, put it inside the reader, and then put that reader inside of that thing, and then put that into your computer, and it has somehow all the like data sheets on how to read the firmware from various kinds of SPI chips. And if you do look that up, it is on a sketchy Chinese server. Is the way you purchase it. that is also why it is $80. It has everything you need for it. Yeah. So, this I should have been earlier actually, but I guess like there's easier ways other than having to manually rip it off. And a lot of devices you can literally just go on the internet and download like a firmware update package and try to pull out the firmware update package from the internet because you don't want to have to deal with any of that hardware stuff. You can also, if your device is something that you can plug into a monitor, just try logging in and asking it to give you files out of the system itself. Additionally, on lower end consumer hardware, it's not uncommon that they just use an SD card to store the firmware. So you just pop off the SD card and you can just put that in your computer and read it. But yeah, these are the next steps after that. So I'll get into the first like communication protocol is on UART, and so it's as simple as you can get. There's a TX for transmit and an RX for receive. So one device transmits, one device receives, and you just transfer bits. There's a bit more to that. So with that FT232 or Hydrobus board before, so you could connect to the TX and RX pins as well as the voltage and power in the board and ground to not short anything. You would connect to all those and you'd run a program on your computer called Minicom. It's an easy one. And the only important thing is you would set up that first thing that says serial device to communicate over that USB that you put into your computer. And there's something called the baud rate. And the baud rate is basically what speed am I transmitting between the devices. It's kind of like the clock rate I mentioned earlier. So there's only a handful of like baud rates and voltages that are used. Like I think there's like 3 sets of voltages I've ever really seen. Like 1.2, 3.3, 5 volts, or only ones. I think really just 3. You can look at the chip and it'll tell you usually. But you pick the voltage you need on the firmware that runs on this. You would pick the voltage that you want to communicate to the chip with, and then on here you would pick the speed that you want to transmit information. And then once that's all done, a lot of times when you power on a device and you have UART running, it'll, if you know, like when you turn on your desktop PC and it prints out like setting up memory and all that junk before it loads up your operating system, that's generally what's hooked up to UART a lot of the time, so you can get that information. And then it's not uncommon at all that it drops you literally into a shell and says, please log in. And in the worst case, you can type in root and you'll be a root user, but hopefully not. So that's generally what that's used for. What's a little bit more complicated but more powerful is JTAG debugging. And so JTAG is a hardware debugging. I really don't want to call it standard. It's a standard as far as there's 4 or 5 standard pins, but there's a whole bunch of different ways that people implement it. Here's just 4 random ones. As you can see, they all have that TDO, TDI, T-clock, TMS. However, they have a whole bunch of proprietary pins bolted on top of it. However, to do JTAG, you really only need these 4 pins. And so you have TDI, which is data in, and TDO, which is data out. You have TCK, which is that clock speed that tells them all how to communicate at the same rate. And you have the TMS, which basically tells it what operation am I going to perform. And so, as you can see, these devices are all daisy chained together. So TDI into this device goes into that next device, into that next device. And so you can actually, with this protocol, have just one header on your board that'll let you communicate to multiple chips at the same time for debugging purposes. So the first thing you'll need to do is, obviously, you're not going to get these nice labeled headers on a lot of boards. You'll just get a set of like 8 to 20 like pins next to each other, and you'll think, I think this is probably JTAG. And so they sell devices like the JTAGulator, and I believe the Hydra bus can also do this basically. And you would connect all 20 pins to these things, tell the JTAGulator which ones it's hooked up to, and it'll actually do guess and check, and it'll go through every possible permutation, and then tell you these are the 4 pins you care about. So it'll guess and check which ones TMS, T-clock, TEO, TCI, and then at the end it'll be, okay, you care about pins 2, 4, 6, and 8, as this was. On this one, it would say you care about pins 5, 9, 11, 15, and oh, yeah, 5, 9, 11, 15. So that kind of is a brute force tool that helps ease that. Because a lot of companies, they kind of make it not easy to figure out their JTAG protocol because it's semi-proprietary, and yeah, that's why it's hard to call it a standard. And sadly, it's a lot more complicated to speak on JTAG from your device as well, but once you know the pins, you would literally grab the same Hydra bus or the FT232, connect to the pins that the JTAGulator told you to connect to, run the JTAG firmware on that saying, I'm connected to these pins, and then that's the JTAG adapter card, Hydra bus. OpenOCD server is software you would run on your PC, and on there, you would give it configuration saying, this is the chip I'm talking to, here's the log file I want you to send it to, and it'll open up a Telnet server or a GDB server that you can just connect to, and then you can literally just run like halt CPU and it'll stop operation. You can run dump memory from this region to this region. It kind of depends on what the hardware manufacturer has put in there, but a lot of the times, if they left JTAG on there, it tends to have operations like set breakpoints, read memory, and standard GDB type commands. Yeah, so that's basically the reverse engineering aspect of it. Additionally, there's protected device where, like, let's say the boot ROM is not in a chip that's readable, so they have a write protect, or they have a read protect on the firmware. So when you try to use JTAG to read it, it'll say, I'm already booted up and I'm not giving you this information because I have a read protect flag on it. So if you run into something like that, you need to do a more active attack to try to dump out that information. And it's generally classified into 3 different levels of invasiveness, which is non-invasive. You don't have to pull off the chip for anything. You can just hook up to the board and it doesn't modify anything permanently. There's like semi-invasive things where maybe you strip away the top layer of plastic, but the chip still works. And then there's full invasive where you melt down each layer of the chip and take photos of it. And I have some brief pictures for what different attacks would look like at each layer. And yeah, 3 different, I guess, like kind of attacks that I'll cover briefly are like fault injection, side channel analysis, optical fault injection, and then decapping. That is way too small. So, does everyone know what stir compare is from programming? Okay, so essentially it takes 2 strings, like hello and whatever the user puts in, or actually, yeah, 2 strings, like let's say you have a password configured on device and you made it password P4SSW0RD!. So stir compare will take what the user inputs and compare it to that string and tell you, yes, did it match this string, or no, did it not match this string. So a lot of people use it to compare 2 strings, and from a security point of view, it's actually an insecure method to do that, and I will explain why. So this was not overlapping on PowerPoint, but if I guess AA, for instance, the way this code works, it'll say, does the first character A match the first character of my actual password, capital P? And if not, stop trying to compare because clearly they're not correct. However, if I guessed PA, it would say, does capital P match capital P? Yes. Does A match 4? No. And so it'll stop there. difference between these two is it did a whole extra comparison, and on a computer that takes longer to do extra comparisons. So you could keep guessing more characters, one character at a time, and start measuring how long does it take each comparison to happen. So let's say it takes this is way too long, but just for ease of math here, let's say it takes 1 second to do a comparison between a character. For this AA operation, it would have taken 1 second to do the comparison. For this PA, it would have taken 2 seconds to do 2 comparisons. So you know that the first character was correct and the second wasn't. So that's a problem both on a web point of view and more commonly like on a firmware point of view, since it tends not to be hardened as quickly. And so we'll talk about why this is bad from a side channel point of view. So on the more fancy end of things you can buy, this is like that $250 board. It has an FPGA on it, and you can hook it up to do trigger on certain events and do all these cool attacks I'll mention briefly, and I basically pulled the pictures from their tutorial slides. So if you get it, you can go through there. So as I mentioned earlier, it takes longer for it to do operations. So this is on the same kind of stir compare thing. So this measured power as your device was running. So literally how much power was your device using. And the red was when it only had 0 characters correct, and the blue is when it had 1 character correct. And I'm not sure what it is. You can see like up until like the second peak here, they look pretty similar, and after that the blue is slightly farther than the red is, up until it gets to the point where it said it was incorrect, and they match up again. So using something like this, you could literally go through character by character and try to determine what the password is. And they have pre-built-in scripts that they want you to run there that basically automatically try to determine that timing difference and put passwords out. Just as a unrelated side note, is this also works over the internet. So I have seen on websites where they use a stir compare, and I was able to force passwords out from the website for like the admin user based on that. Essentially, the way you fix it is you hash the passwords before comparing those. So just a side note. So the next kind of thing that that device can do is called clock glitching. And so the way a computer works is it has instructions that it runs. So it literally will run one instruction at a time. But in order to know what instruction it needs to run, it'll grab the bytes and decode the bytes into the instruction it needs to run. That takes time, and in order to make it faster, you can see they have these 2 lines here where they, while they're running something to execute an instruction, at the same time, they'll load the next instruction into the decoder. So when they call the instruction that they want to run, it's already been decoded. This is a problem for attacks like clock glitching because if you remember, I said that clocks tell how fast you want it to be. So it says every second I'm going to do 1 operation. So every second I'm going to execute the next instruction and start decoding one after that. So if you can influence the clock with that blue line there, you can see another peak. The chip itself will get messed up and say, oh, I went high again, so I need to pull in the next instruction. But it won't have time to actually run the program counter and do the instruction coding before it gets the signal again, okay, load the next instruction. So because of that, if you time it correctly, you can have it so that it's decoded the next instruction, but it has not executed yet. So it'll skip over to, you can see like it says, load 2 before it's executed. So, and then when it loads 3, it executes. So it's off. Yeah. Additionally, there's voltage glitching. And this is literally not giving it enough power to do what it needs. So an easy example of this is if you can think of any time you need to write something into memory, it'll take a certain amount of voltage to write it into memory. Is the easiest way to think of it. So if, when it's trying to write an important variable out to memory or out to like a register, you take away the power, you literally drop it to VCC for a certain period of time, it won't successfully complete the write, and because of that, it'll be something that's not different. So, for instance, if you had a stir comparison for a password, and you had a variable at the end that says, did my password match, yes or no? Let's say it started off with, yes, my password matched, but if it was incorrect, it changed that variable to no. So if you glitched it, so it couldn't actually write that variable to no while it was running, you would essentially, at the end of the function, it would return saying, yes, my password is correct, because you stopped it from performing that write operation. And it's very sensitive to get this correct. And the reason why you buy the $250 board at the FPGA is you can actually sync it up with the clock of your computer. The FPGA lets you trigger on specific events, like down to like very fast speeds. I don't know how fast it goes, microseconds. And yeah, so it lets you kind of guess and check. And this is kind of just a picture of, you can see like if someone were to take away voltage at this point in time, it wouldn't be over this threshold to perform a write. It's the best way to think about it. That picture makes a little more sense where the voltage affects where the drive goes for being able to perform a write operation or not. And towards the end, we have very invasive attacks that are very dangerous, so don't do them at home unless you have a fume hood, which is chip decapping. And essentially, around your chip is made out of silicon, and around the silicon is plastic, and those plastics dissolve with acids that your chip will not. So, like a example of one would be like nitrous oxide. If you dump your chip inside of that, you can boil off all the plastic, clean off the top of it, and you'll have a nice chip, a nice clean chip. And the reason you would want that is people literally take what are called scanning electron microscopes, and they can record, they can take photos at even more precision than you can see optically. Yes. So, like for instance, that picture on the right there is an example of someone's memory. So there's people who've literally written computer vision algorithms to read out, is this box a 0 or a 1? So they'll rip off the top layer of the chip and literally read each bit off of it and then reconstruct it into a binary to get the data back. And this is not something you can do at home because the equipments are expensive. Well, I think you can rent them at UW for like $100 or something. So, 120 an hour? Okay, yeah. So yeah, you can rent a scanning electron microscope if you have a decap chip and go all out. I have not had to perform this kind of stuff before, something that's beyond me, mostly because I don't really have a safe place to. Yeah. If you put this in acid, I just want to reiterate, it'll put off toxic fumes that you don't want to breathe. The plastics dissolve into not nice things. So you need a fume for that. And then on here on the left is an example of a nice clean like dye on the back of a chip. And on the right, you can see circles. Some chips actually come like they're built with the silicon on the back end, like something wafer level. Anyways, there's some chips that if you look at a PCB and you like rotate it, it looks shiny like a mirror. And something interesting about these is silicon is actually a conductive material, just by its use in chips. So there's an attack called optical glitching, where if you literally shine a laser at a silicon die, it will actually change operations. You can flip bits from 0 to 1 inside its memory, for instance. So people build these things where they literally get like a CNC board or a 3D printer and just rip out the 3D printer, attach essentially a laser pointer to the top of it, and have a robot will shine the laser at very specific, like millimeter offsets on it at specific times, so they can say the same thing of like flip the security bit from 0 to 1 at this point in time. And a really famous example that you can see online from that, where in the real world someone ran into it on accident, is they were taking photos of, I think it was their Raspberry Pi with the flash camera, and every time they took a picture of it operating with the flash camera, it was rebooting itself because the chip was sensitive enough to the light from the flash from the DSLR that it was rebooting the device. So you can imagine being able to control that down to a level that a machine can point a very precision laser on a specific place on the die. That's kind of why this would be useful. Yeah, that's everything.